This is part 2. If you have a sequence of functions converging uniformly and everything in the sequence is continuous, then f is continuous. And it's a straightforward, it starts off as a straightforward continuity proof. Fix the c, let epsilon be bigger than 0. Then we need to prove f of x minus f of c is less than epsilon. And to do that, we add 0 twice basically, so we get f of x minus f sub n of x plus f sub n of x minus f sub n of c plus f sub n of c minus f sub c. Now, I used uniform continuity right here. In fact, maybe I'll write it down. We can do this. Since f sub n converges uniformly to f. So I've been able to pick a capital N such that f sub capital N of x minus f of x is less than or equal to less than epsilon over 3 for all x in A, which includes c and any other x I pick. So it includes this x, this is less than epsilon over 3, and includes the c, which is less than epsilon over 3. That's the power of uniform continuity. This 1n works for anything. It works for both the x here and the c here. And note, I'm using a less powerful version. Normally you'd use f sub little n for some little n bigger than or equal to big N, but I don't need that. I just need a single function here that works. Then I can use, since now my big N is fixed and defined. Since big N of x is continuous, there exists a delta bigger than 0, such that I'm just using the definition continuity. X minus c less than delta. C is defined, I defined it right away, implies fn of x minus fn of c has to be less than epsilon over 3 as well. That's just the definition of continuity for this particular function f sub n, and I got the capital N from the uniform continuity. So that tells me that this bit here is less than or equal to epsilon over 3. So that gives me epsilon over 3 plus epsilon over 3 plus epsilon over 3 less than epsilon. So what did I do? To summarize. Okay, I'm going to prove that f is continuous, which means fix the c and let epsilon be bigger than 0. I'm going to prove that f of x minus f of c is less than epsilon as long as x minus c is less than delta. To do that, I'm saying, okay, because it's uniformly continuous, I know that there's a capital N such that for all little n bigger than it, you get f sub little n minus f is going to be less than epsilon over 3 for all x. But I don't even need those little n. I'm just going to stop with this capital N. So I'm not even using the full power of uniform convergence. So just get that big N. Now that I have that big N, this is a single function. So, and I know it's continuous, so there exists a delta such that whenever this is true, it implies that fnx minus fnc is less than epsilon over 3, since it's continuous at c. And now I throw it all together. X minus c less than delta. The delta came about from the fact that f sub nx is continuous. Then fx minus fc is equal to fx, I'll jump up here, fx minus f sub n of x plus f sub n of x minus f sub n of c plus f sub n of c minus f of c. And notice that this just goes to 0 and this just to 0, so this is really the same as this. But then I can use a triangle inequality. Fx minus fn at x plus fn at x minus fn at c plus fn at c minus fn, or minus just plain old f of c. This is less than epsilon over 3 as long as capital N, well, that's basically always true for capital N. As long as the inputs are the same, you get less than epsilon over 3. The inputs are both x, so we're set. Similarly over here, fn minus f is going to be less than epsilon over 3 as long as the inputs are the same. The inputs are both c, so we're good. Finally, since fnx minus fnc, because fn is continuous, I know that this is less than epsilon over 3. So I get fx minus fc is less than or equal to, less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which equals epsilon. So f is continuous in A, and we're done.